Good morning, everybody. Thank you for rejoining us. It's my big pleasure to introduce now the rector of the Autónoma University of Madrid, who was so kind to come and share with us this very emotive session of the IFIMAC Day. Okay, Amaya, your turn.
Okay. Thank you very much, and sorry for taking some of your time for this second session of the day. Thank you, Ruben, for once again extending the kind invitation to participate in IFIMAC Day with lots of researchers from the Institute. And although I couldn't be here this morning to give the opening remarks for the day, I didn't want to miss the opportunity to be here with you today, especially to congratulate Professor García Vidal and Professor Gómez Herrero on their awards by the Spanish Royal Society of Physics, whose president is here with us chairing the session. I'll get to that in a moment, but first let me congratulate IFIMAC for putting together a program that reflects the excellence and dynamism of the IFIMAC community. The morning began with a session dedicated to young researchers who have recently joined the Institute. I'd like to thank you for your commitment to mentoring the next generation of scientists. A generation with a bright future ahead, standing on the solid foundations laid by IFIMAC's experience, I wouldn't say old, experienced researchers. Over the past decade, IFIMAC has evolved from an ambitious idea into one of Spain's most respected and prestigious research centers, a place where curiosity-driven science, collaboration, and international excellence converge. Its past is a story of visions and perseverance. Its future, I'm certain, will be one of continued growth, innovation, and impact. A future built upon the founding work of researchers like those that have been recently recognized and whose achievements you're about to hear about. Professor Francisco José García Vidal, recipient of the 2025 Gold Medal, will share his personal journey through 3 decades of groundbreaking research in nanophotonics. His work has not only advanced our understanding of light-matter interactions, but has also helped define an entire field of study. We celebrate the gold medal today, but he has also received Spain's highest recognition of research in physics, the Blas Cabrera National Research Award, that this year has been awarded to another UAM physicist, Professor García Bellido. He has also received the Miguel Catalan Regional Research Award, among many other recognitions. So congratulations, Paco, on your outstanding achievements. We will also hear from Professor Julio Gómez Herrero, that has received the 2025 Award in Physics, Research and Innovation, and his pioneering work on scanning probe microscopy has opened new windows into the smallest of the small, the Nanoworld. These awards, and I'm sure Professor Viña will tell you more about it later, granted by the Spanish Royal Society of Physics and the BBVA Foundation, are a testament to the impact and the relevance of the research carried out at IFIMAC, and in general to the good health of physics in our university. So, as well as congratulating them, I'd like to extend my warmest congratulations to all of you, to all the IFIMAC researchers, for your dedication, creativity, and scientific rigor. Your achievements not only elevate our university, but also the broader scientific community. And they have earned you the María Maeztu Seal of Excellence on 4 consecutive occasions. It's a huge achievement. We must now build on this legacy to keep growing and take science to the next level. I'm confident that the coming years will witness that leap and that you will continue making a decisive contribution to our university's international reputation in scientific research. To finish, let me express my sincere gratitude to the organizers of the IFIMAC Day, to Ruben and to the board of this research center. Your efforts make it possible for the scientific community to come together, to exchange ideas, and celebrate excellence. So thank you very much for making this day possible. And before I will pass the floor to Professor Viña, I'd like to call Professors García Vidal and Gómez Herrero to the stage to give them a round of applause.
So we go back to English. Thank you very much, Julio. Thank you very much, FJ. Thank you very much, Amaya, for your talk. It was very adequate too. Now, when I was invited to chair this session, I say to Ruben, I never use 2 hats here at the university. And it's true, I never use my president of the Spanish Physical Royal Society when I'm giving classes or when I'm doing anything. But today you forced me. I mean, I told him, I mean, you put a president of the Spanish Royal Society, so I have to do a little bit of propaganda, so to speak, right? So for those that you don't know, I looked yesterday, actually I looked this morning, we are 3,997 members, which you say is, as a physicist, is that low? Is that big? It's low. It's very low. I mean, you can say it is low because you compare with other societies. It's not easy to compare because the numbers are not there. The only numbers that you can find if you look in the web are those of the German Physical Society, and they are 55,000. So that means that if we normalize, we should be at least a factor of 3 more. So it will be something like 12,000, 1,300, or something like that. As a matter of fact, this is a problem. I was a couple of days ago in the foundation, in the BBVA Foundation, with the prizes of the Royal Spanish Mathematical Society, and the director of the foundation, Rafael Pardo, insisted again, I agree completely with him, that Spain is a country where associationism is not is not well done, right? I mean, we don't do it, but it's the only way to do things. So let me tell you a little bit more about the society and see if on Monday at least we are 4,000, right? So it's 3 more. For those of you who are not, I'm very modest, as you see, okay? But I mean, we have 25 groups and divisions, right? 11 of them together with the Royal Chemical Society, Spanish Royal Chemical Society. Among those, the most active, the most numerous, and I'm very proud to belong to that, and I was member of that since I came back to Spain and I joined the Spanish system, is what was called JEFES, which is now called Division of Physics of Condensed Matter. Both of our awardees today are members of this division. It has a big number. It has 782 members, so it's 20% of the society. Among those, a lot of them are students. Something like 170 are students, okay? And the rest are senior people. We also have another division, which is the division of theoretical physics and particles, which used to be, in the past, the biggest one. Now is the second one. No, it's the third one. Has 16%, 642 members. And what is amazing, what is really amazing, and here you are young people, is the group of students of the Royal Physical Society. This is now the second one. It has 729 members. It was created 6 years ago. So in 6 years, has done much more that we are, I don't know, 25, 30, 40, it depends where you put the origin of that. So students, there is something that you can join is the group of students of the Royal Physical Society. Okay, they are very active. They are extremely active. The only problem is that this association is very volatile because they are not students anymore. And I don't think it's so expensive to go from 12 euros to 35 euros to be a member of the society. But many of them, I don't know, maybe they go abroad for, not many, because I mean, they are not all go to academia, but they don't stay there. But okay, so if you think of that, I mean, they organized last year the planks competition, if you know about that. They are doing this year in Valencia their third national meeting and things like that. Okay, so they are very, very active. Okay, we have other groups like astrophysics, which is big number. We also have a division of outreach and teaching of physics. It's a group which is growing a lot now, also, which is the group of quantum technologies, okay, which is now recently created and has already 370 members. And also we have another division, which is the last one, which is of complex systems, of statistics, nonlinear and complex systems. And also, I think it's very important, we have a group of women in physics. That is not a group made only by women. It's a group which is dealing with the role that women should play in physics. It's male and female members, mostly female, but all of those who are there are trying to help and break this gap between males and females. And they are also very active too, okay? So, you know where we are. We organize many things. Next year, the meeting, which has gained a lot of impulse also thanks to Jefes, okay, and the talks organized by the Jefes group is going to be in Seville in July. So it's a good place to go, but there will be air conditioning. So I hope that you are there. Okay, but now enough for that. Now we want to make this session about the 2 awardees. I'm going to present the first one, then we will go down, and then I will present Julio too. So let me start with FJ, and I'm very glad that what he was saying, I mean, we didn't talk about that, but it was exactly many of the words he used. I was thinking, and they were in my mind, and I was thinking of I didn't write it down, but I wanted to use them too, okay? Let me first bit think of the curriculum that already Amaya said about that, and he also mentioned he graduated in physics in 1988, PhD in 1992 under Professor Fernando Flores and Álvaro Martín Rodero. And this is one of the points that FJ mentioned. I think is very important. I mean, this does not come out of the blue, okay? It comes because many years ago there was a person here who was Nicolás Cabrera, okay, and we have an institute which called the Institute Nicolás Cabrera, who was given the task to build physics at this university. And I think we all think that he did a very good task, okay? He hired people like Fernando, like García Moliner, who passed away recently, who was member of, at the beginning of the university, and then he was a member of the Consejo, but the Consejo and the university at that time were entangled very much. And thanks to these people, and thanks to Nicolás Cabrera himself, okay, because that is what we say now, the C5, right? But in the C3 was Nicolás Cabrera, okay, and he was very much fond of experiments, and he created the surface physics lab, and thanks to that, we arrived to things like what Julio and many other of his colleagues are doing now there. So it doesn't come out of the blue. I mean, it relies on all that, okay? Okay, so coming back to FJ again, he had a Marie Curie fellowship at Imperial College with John Pendry, and then he came back and was associate professor here until 2007, and then, no, 2007 full professor, I guess, right? Well, as we all know, he was founding director of the Condensed Matter Physics Center, IFIMAC, president of the Spanish Physics Committee of the Spanish Agency for Research. He got an advanced grant in 2012. He has been associate editor in Physical Review Letters, fellow of the American Physical Society, and among the prizes that Amaya mentioned was the Jaume I, the Blas Cabrera, and the National Prize in Physics, and I think what is Miguel Catalán also, and I think what is more important now, the medal of the Spanish Royal Physical Society. And now I read what the jury thought that was worthwhile to give the prize to FJ, and I read literally, it was written in Spanish, I gave it to Deep L to translate it into English, but it's well translated, okay, I check it. So the jury highlights his excellent scientific career with highly influential contributions in nanophotonics, plasmonics, and metamaterials. Among his main achievements are advances that allow light to be manipulated in ways that were unknown until recently, with applications in sensors and communication devices. He has also demonstrated new mechanisms of molecular modification through light, with possible applications in solar cells and chemical reactions. His ability to inspire numerous experimental groups to verify his theoretical predictions is also highlighted. FJ, the floor is yours.
Okay, so this is the first 30 plus. I mean, that is not a particular year to start all this nanophotonics. Okay, so this is okay now. No. Okay. So this is the outline of half an hour. So basically, first I'll try to introduce classical photonics. I mean, you have heard about these photonic crystals, plasmonics, and metamaterials, and then I will talk about, let's say, three, let's call achievements of my career. Yeah, I feel like an old singer, no, that is singing the best, the hits of his career. So, okay, so starting the transmission of light through subwooden apertures, then the concept of what we call a spoof surface plasmons, and then lately quantum nanophotonics. Okay, so classical nanophotonics, I don't know, 1990. So basically the goal in classical nanophotonics at the beginning of the 90s of the last century was to tune, tailor material properties and geometry. Geometry is an important point in this, to control the flow of light at length scales smaller than lambda. So the driving force in this area of research was to try to control the flow of light at the micron scale in order to achieve, let's say, photonic transistors. No? The idea at that time, people were talking, oh, we have to reduce the size, so we have to create a kind of photonic circuit. So we have to go down to dimensions to go to the wavelength of light. So basically, this is the typical way to talk about this travel of 30 years. So basically, everything starts, I mean, this is epsilon, that is the dielectric response of the system, and mu, that is the magnetic response. So basically, the first concept that appeared was these photonic crystals, in which you operate in the first quarter, in which you have positive epsilon and positive mu. Then people started looking into plasmonics. In plasmonics, you rely on metals, and metals, as I will show you, basically they have a negative epsilon and positive mu, okay? And then the most novel thing was the concept of metamaterials, in which you can achieve materials in which both epsilon and mu is negative. You don't have these materials in nature, so you have to create new materials that are so-called metamaterials. Okay, so let's start with photonic crystals. So basically, the idea is quite simple, no? In atomic crystals, electrons behaves as waves. So basically, the movement is governed by interference and diffraction. So then you have bands. And depending on basically the scattering of the electrons with the periodic potential of the nuclei, you can have different situations. You can have an insulator in which the conduction band and the valence band are well separated in energy. You can have metals in which you have an overlap between the conduction band and the valence band, and then you have conduction. And you have semiconductors in which you have a gap between the valence band and the conduction band, but this gap is only of the order of 1 eV. So then you can go from the valence band to the conduction band. So the idea was to create, let's say, semiconductors for light, to create something in which you have a photonic band gap. So, and what is the idea? So the idea you replace the periodic potential of the atomic crystal with a periodic modulation of epsilon, in this case. And then you have to periodically modulate epsilon in distances of the order lambda. So then, as always in science, in physics in particular, at that time, I mean, it was possible, not before, but it was possible to create, let's say, photonic crystals. It was possible to manipulate materials in length scales of the order of microns. So, as always in physics, no? So you have experiment theory that at the same time they converge to achieve something. No? And then you have this periodic modulation of epsilon, and accordingly you can have photonic band. And depending on geometry, and geometry is an important point here, you can have some regions in which you don't have light. For those particular frequencies inside this band gap, you don't have photonic. It doesn't mean that it's black. It means that you cannot have a photon. Even if you try to switch off the light, somebody turns off. Okay, so it's you cannot have light there. So then this is interesting because then you can operate like any semiconductor. So basically you have a photonic insulator. You send light from here. Basically, light cannot penetrate into the system. And why is it interesting to have a photonic insulator? The point is that now you can do different tricks. For example, now you have a photonic crystal in 2 dimensions. This is basically rods. Then you can create a line of defects, okay, in this system. And if you send light inside, oh, sorry. Okay, you can see that you can turn around. I mean, light in length scales of the order of lambda is very difficult to make rectangles. In this case, you are able to do, oh my God. This is very old simulation, so probably this is the reason. It's not compatible. I mean, this is from the 90s, so probably it's not compatible with this software. So then, because light can only exist in this white guide, you can turn around. I mean, and the distance is of the order of lambda, so you can turn around. And you can use this idea to, for example, create optical fibers. This is a bulk photonic crystal with a band gap, and then light cannot exist here, so it's guided through the hole, through the core, and then you can bend your optical fiber wherever you want. Okay. Okay. So plasmonics. So 96, I put that year because this is the year in which I returned from UK. So basically, the electric response of a metal is governed by the free electron plasma. No? So this is the typical Drude formula. And the important point is that below the plasma frequency, epsilon is negative. So if epsilon is negative, it means that the wave vector is purely imaginary. So a metal is a natural photonic insulator. Okay. So, but this negative epsilon has another interesting consequence, is that if you now create a hole in a metal and then use light from here, basically, first what you have is diffraction. No, light is diffracted in all the propagating waves. But also you can see here that you have something that is propagating along the surface. Okay? It's evanescent light, let's say. You cannot see, but it's basically an electromagnetic field that is running along the metal surface. And this surface electromagnetic mode is called surface plasmon polarity. So the important thing about these surface plasmon polaritons is that this is, let's say, the dispersion. The rector is not here now, so I can elevate the level. So basically, this is the dispersion relation of the surface plasmons. So omega versus k. And basically, this is the light line. So it's basically c multiplied by the momentum. So then, for low frequencies, basically, it's the light line. So, but for frequencies of the order of the plasma frequency divided by the square root of 2, you have these flat regions. So, and importantly, in all this region, that is the optical regime, you have something that is far away from the light line, and then you have electromagnetic field. This implies that the electromagnetic field is highly localized into the surface. Okay. Good. So this is the typical numbers. This is the typical number that we put it at the beginning in order to sell that you could create Now it's a bit old, like me. So basically the idea is, we have good numbers. So basically you can describe the propagation characteristics of the plasmon by 3 numbers. How much decay into vacuum, how much decay into the metal, and the propagation length. Always in physics, when you have something interesting, you have a price to pay. You have negative epsilon, you have losses. So the problem of these modes is that you have losses. And then the propagation length is finite. So for example, if you work with optical frequencies, but the propagation length is not so bad, it's 40 microns. Okay? Not bad. I mean, you were thinking in creating circuits. But it's not bad. The decay into vacuum is sub lambda, is 0.5 lambda. Even for telecom frequencies, for 1.5 microns, the decay into vacuum is not sub-wavelength, but the propagation length is extremely high. It's 200 times the wavelength. So there were plenty for always in plasmonics. There is a trade-off between propagating length and transversal confinement. These numbers are for a 2-dimensional surface plasmon polariton. And the problem is that when you try to squeeze the surface plasmon in 1 dimension in order to create circuits, this number is strongly reduced. So at the beginning, people were looking at different things, and at the end of the day, the best architecture to create photonic circuits based on plasmons were these so-called channel plasmon polariton. Basically, you have a metal fin, and then you create a B groove. And in this case, the trade-off between propagation length and confinement is extremely good. Apart from having this propagating plasmon in 1 dimension, or 2 dimensions, you have localized surface plasmons. So if you have a metal nanoparticle, you can have also a surface plasmon polariton localized. So an important point of this localized surface plasmon is that the electric field is extremely localized at the surface of the metal nanoparticle. Then people have been using these localized surface plasmons for sensing. Basically, this is the work of Roman Kiraniki, and I'm not going to enter into details. So the third concept is metamaterial. So it's around 2000, more or less, 99, 2000. So here, at the end of the day, you look into this slide and you say, it's so simple. So the idea is, you think in a conventional material, the atoms are located at distances that are much smaller than lambda. And basically, when light propagates in a normal material, it's not able to see the atoms, basically. So, but at the end of the day, the optical properties are dictated by their atoms. I'm not able to see, but the optical properties are dictated by basically the atoms. So the idea of metamaterials is, we have plenty of space. So what about creating a metamaterial in which we replace the atoms by meta-atoms? You design the meta-atoms in such a way that you construct a epsilon and mu at will. Well, this is, at the end, it's a very basic idea. So, as you probably know, can achieve with this idea negative refraction by creating materials with both epsilon and mu negative. And also, of course, you can create invisibility cloaks. So before going to enter into the 3 main achievements, I'm going to tell you a story about this. So we publish, because I think there is a moral in this story. So in 1997, we published a paper in UK, at Imperial College, in which, it was, even the name metamaterial, it was not coined. So, but it was in the, I don't know. So we decided, what about looking at the optical properties of a system made of carbon, like the carbon nanotubes, but instead of having carbon, what we thought is, perhaps if we have carbon, but that is less dense, the idea was perhaps you can allow light to penetrate and being absorbed in the bulk. So this is the idea. So you have carbon and vacuum, you have an impedance. So the idea was to reduce the impedance mismatch between the system, but at the end of the day, they are carbon, so they're going to absorb. So this was the idea. So we published PRL. We were very happy at that time. Now it's becoming very difficult to publish in PRL. So, okay, so we published, we received some citations. That's all. That's it. This is the life of a theoretical physicist. You publish something, but 10 years after, an experimental group in New York, a bit without contacting with us, they were able to create these things, these carpets of carbon nanotubes. And they put it here, no? And then the darkest man-made material ever. And they even put this material in the Guinness Book of Records because it was the darkest man-made ever. So, even I was approached by the TV, by the radio, by the newspaper. There's an interview in El País about this kind of thing because my name appeared here in the abstract. Because it was the theoretical, it was the experimental confirmation of this idea. But you can see, I mean, we were collaborating with these guys in some way, no? In time and space, no? Basically, the guys were really far away from us, and it was 10 years after. So I don't know if the guys read our paper, and then they took them 10 years to do the experiments. Okay. But there is more funny about this story. Okay, I don't know if these guys patented the idea or not. I didn't patent the idea. But 5 years after, a company make a paint based on these carbon nanotubes. It's Banta Black. And then you can put it in satellites. And then if you want, you can buy a BMW painted with carbon nanotubes. It's extremely expensive. But, okay, you can buy it. And more surprisingly, an artist, this guy, bought the patent for artistic demonstrations. Okay? And then you can go to some exhibitions. Now it's called installations in art, no, apparently, in which you can see, basically, for example, in this case, you put this painting, whatever, and then it's like vacuum. No? And then there is... So what? I mean, this is... You publish a PRL paper about carbon nanotubes, something that you think that is very academic, and at the end of the day, a guy like this bears an exhibition on that. So theoretical physics is marvelous. Okay, let's go to the standard optical transmission through subwavelength apertures. Okay, the transmission of light through subwavelength apertures is a very old problem. It's really amazing to find that the first calculation of how light transmits through a hole was done in the 40s of the last century by Bethe. And the Bethe theory demonstrated that when the diameter of the hole is much smaller than lambda, basically the transmission normalized to the light that is impinging into the hole goes like A over lambda to the 4th power. Okay? So basically it implies that if A over lambda is very small, then the transmission is extremely small. So, and on top of that, light that is emerging from the hole is diffracted in all directions. Okay? So few light is going through the hole, but this light is going into all directions at the exit side. This was the common knowledge until it appeared this paper in '98, in which a group in Princeton at that time, the Thomas Eversen, they were showing that if you put the holes forming a periodic array, then you have some transmission peaks in which the transmission, you can see that basically the lambda is of the order of the period, basically at around lambda of the period, you have a transmission peak. And in this transmission peak, the transmission is much higher than expected from Bethe theory, orders of magnitude. Okay? So, okay, at that time, the machinery was in place, so we tried to simulate it. But we couldn't, now you can go to COMSOL, and that's all. But at that time, we couldn't do the three-dimensional case. We had to do the one-dimensional case. We were poor. I mean, nobody could do it. So we did the one-dimensional version. I mean, instead of having a 2D array of holes, we had a one-dimensional array of slits, basically, with Juan Antonio that is here. So basically what we found is that you can indeed have some transmission peaks around the period of the array. Okay? Of course, here you have other peaks that are the physical origin is different. But these peaks that appear in the transmission spectra, basically, when you look into the field, basically what you are seeing is that you are setting a surface plasmon on this side and another plasmon on the other side. But the field intensity is very small inside the hole. Okay, so nice. So it seems that the plasmons are involved, surface plasmons are involved in this process. It took us 2 years to do the 3D case. And basically what we found is that this basically is like quantum tunneling. Basically the system coming from the left excites a plasmon. Now the coupling between this plasmon and this plasmon is exponential. Then this plasmon is able to excite the other plasmon, and the other plasmon emits light by scattering with the holes. Okay? So this is the physical mechanism, and you can see here a film in which hopefully you will see. Basically what I'm representing here is the electric field in this plane. Here is a zoom, and here is a wider version. And then you will see that no light is going through the holes. So I don't know if I can. See. You can see? Versus side this one, then the one, and then plus. I'm going to put it because it took us 3 months to prepare this. Okay. So basically, we found with this theory that the phenomenon was based on surface plasmon polaritons, but the key ingredient was the fact that you have a Hall array, you have periodicity. Okay. So because if you send light to a metal surface, you are not able to excite the plasmons. You can see in the dispersion relation, there is no overlap between the light line and the plasmon. So you have to create periodicity to fold them down the first billion zone. Okay, solid state physics. Okay, so the idea you needed the holes in order to excite the plasmon on the entrance and in the output surface. Okay, so then the idea was clear. What happens is you have now a single aperture surrounded by periodic corrugation, or the so-called bull's-eye geometry, in which you have one hole and then some periodic corrugations. As expected, so this is the result of the simulation. You see that as a function of the number of corrugations, you start seeing a peak, a nice peak that is related to the excitation of the plasmons. This is nice, but what is more surprising is that if now you put the periodic texture on the output side, then the total transmission doesn't change. So the total transmission is basically controlled by the input corrugation. But however, when you look into the output side, you see that instead of having diffraction, you are able to create a very collimated beam in the forward direction. And not only a collimated beam, this is 2 degrees, but also a focus. And a focus that appears at 40 microns. Oh, so we decided, wow, this is really applicable. This is my only pattern. Okay, this is applicable. You have a focus. I spent several months talking with the guys here in the Vice Rectorate to make a pattern. But no application. So when you look for applications, no application. When you do not look for applications, there are applications. So basically, the message is you have to fund basic research. Okay, so with this idea of putting corrugation in the input side, on the output side, indeed, you can overcome the diffraction limit of light passing through subwelling apertures by corrugating input and output surface. Okay. Then we demonstrated that this phenomenon was really general. So this could appear for photonic crystal waveguides, for matter waves, and even for acoustic waves. So it's the only ingredient that you need is basically surface modes. But we got something, so we have this result since 2021. But what we found, and we had this result, but we didn't publish. So we did the first calculation with silver. No? That is the typical metal for optical frequencies. But also, because we are theoreticians, so we can put the epsilon that we want. So we put here is called epsilon equal to -infinity. So a perfect conductor. And for a perfect conductor, you have 100% transmission. 100% transmission. Okay? You're able to see through the metal. So then we contacted. So this implies that this phenomenon could also appear in other frequency range in which metals behave as almost perfect conductors, like microwave terahertz. So then we contacted with an experimental group in Pamplona that they were able to do it in the microwave regime. So now, instead of having periods of the order of 500 nanometers, they have periods of the order of 1 millimeter or 5 millimeters. Okay, so they are big. And then, as our simulations told us, you can have 100% transmission for those frequency range. But in our mind, there was a problem from the fundamental side. And the problem is the following. There are no surface plasmons in perfect conductor surfaces. So this is the experiment, the numerical experiment that I showed before. You have a hole, and then you have a metal film, then you have the surface plasma. If you do the same for a perfect conductor, basically the only thing that you have is diffraction. You don't have a surface plasma polarity. And that is a problem. That is a problem. Because if your explanation in the optical regime relies on surface plasma polaritons, and the phenomenon appears in the perfect conductor, and there are no surface plasma polaritons, you have a problem as a theoretician. But the answer came after all the appearance of metamaterials. The idea is the following, that geometry itself creates surface electromagnetic modes. So if you have a perfect conductor, and then you put a two-dimensional array of holes, then the effective epsilon, in the metamaterial sense, when lambda is much larger than D or A, basically is like the Drude formula, in which you replace the Drude formula by just the cutoff frequency of the whole waveguide. So then you are creating a meta-metal in some way. So you have a finite epsilon in this case. And then if you have a finite epsilons, you have surface plasma polarity. And after so much thought, we call it a spoof surface plasma. Okay, but now you can imagine, this was really interesting, because then all the phenomena that you found for surface plasma in the optical regime, you could transfer to lower frequencies, everything. So then we started, and I'm going to pass very fast, doing things with this kind of idea. No? So for the simplest is that you have just a metal cylinder, then by creating corrugations, you can have some modes like the plasmons, and then there is experimental realization in terahertz. Then, because people in the optical regime, they were working with B groups, we decided to do a periodically B group. No? So you have in which it's going like that. You introduce a modulation in that regime. Then, okay, we were really creative. Antonio is there. So we got this tablerone, I don't know, wedge in which you have a corrugation in the input side. So you have also metals. And then this is new. Diego is here also. So the so-called domino plasmon. So basically, there are parallelisms in this way. And then the point is that the dispersion relation, it was insensitive to L. Okay? So then you can focus all the light that it was in the very wide dominoes to a very narrow domino. You were able to concentrate light because the dispersion relation, it was the same. And then the final, okay, this is 1 pound, okay, in the microwave. So then this is the ultimate thing. This is what we call conformal surface plasmons. Diego is here also. So basically, we found that even the simplest geometry, that basically is a cam, is a peine. Okay? So you have corrugation. We found that the existence of these spoof plasmons was independent on the width of the metal film. And then you can have even for really very thin metal films. And then it was experimentally realized by the group of Tijun Chui in Nanjing. And the good point about this, what we call conformal surface plasmon, is that basically this is why we call conformal, that you can bend completely the waveguide. If you try to do this at home with a normal metal waveguide, light is scattered. So the point is that because light is so concentrated on this region, then it's able to adapt to the size. Okay, very fast. We also found that you have a spoof localized surface plasmon. So the idea is at the end when you see the image is very simple. So you have a localized surface plasmon in a cylinder in the optical regime. So you want to create a spoof localized surface plasmon for a PEC. What do you have to do? Introduce corrugation. So you introduce a corrugation, and then there is a nice, for a theoretical physicist, I mean, you compare this with that. Exactly the same. Exactly the same. Normalized to the appropriate frequency, but it's exactly the same. And then it was also experimentally verified by the group in Nanjing. So you have, the thing is that now you have all the machinery. You have propagating a spoof surface plasmon and localized spoof surface plasmon. So then you can do a spoof surface plasmon photonics. So you have all the ingredients. And people started to do these kind of things, to use a spoof conformal plasmons, a spoof localized plasmons, to do wireless body sensor networks based on metamaterial textiles. Okay? And the point is that if you compare, I mean, you want to send light from here to here or communication. If you try to do with just an unpatterned conductor, there is no way to go there. But with these spoof plasmons, the conformal surface plasmon is adapting to the geometry, and then you can send light from one place to another. In this case, it's microwave. This is a kind of proof of concept, and this guy is a group in Singapore, and apparently it's funded by the Singapore Airlines to put in your seat all these things in order to measure your vital constants when you fly. So again, if you see the evolution from there to there, it's not amazing? So here is a fundamental problem. 3 years thinking about these kind of things, you end up with something that is even aesthetically nice. And then some people in Singapore, they decided to do, okay. Okay, I think that I'm going to skip this last version and the important transparency or slide. I don't know how to, sorry. I have to put my glasses. No, I cannot. Okay, I'm going to go very fast because the important, so the acknowledgements. This is the important part. So I'm going to take off my glasses. So basically, I have to acknowledge, I mean, I didn't do alone. I mean, everything started with my postdoc now is Sir John Pendry. Then I started collaborating with my longtime firm, Luis Martin Moreno. And then I collaborated with so many experimental people. Thomas, in particular, Thomas Evesen and Tijun Chui. Okay. I think that I like this way of working in theoretical physics. You do something and then you test experimentally. You create something new. And of course, it has been a personal but a very accompanying journey. I have to acknowledge all the people here. The first one, Juan Antonio, when he returned. Then Jorge, Esteban, Antonio, Johan Christensen, Diego Martin Cano, Paloma, well, all these things, Javier. All these in red are members of the IFIMAC now. And these are, Jaime is my last PhD student, Alberto, Maxim, Jaime, Carlos, Francisco. And this is, if you want to know more details about all these things, you can find it in these 3 papers. And thank you all.
Thank you, FJ. We have time for a couple of questions, comments. Juan Antonio.
Thank you very much, FJ. I really enjoyed it. Okay, well done. So just for fun, do you think there will be a Nobel Prize, essentially, metamaterials?
Well, it depends on the lobby, no? I mean, so now, I mean, apparently in the last lottery of Nobel Prizes, I mean, people were thinking about, I mean, they were thinking about giving to John Pendry, of course, and David Smith and Capasso, because now it's, I mean, apparently now in the Nobel Prize, I don't know, at least in this area of research, you have to find an application, no? And always an application or something, no? And it's true that all the hype of the photonic crystals, or plasmonics, I have to say, were done because basically nowadays, although at the beginning people were thinking that plasmonics were going to be used for photonic circuits, clearly it's not the final thing. So, and at the end of the day, the only application of plasmonics was or is sensing. That, by the way, it was the only application that it was for metals even before plasmonics name was put in the market. Okay? But what is true is that now people are doing, they have put the concept of metamaterials to 2 dimensions, and they are creating meta surfaces. And apparently they can do very nice things with meta surface, control the flow of light and change the phase. And now people are thinking that perhaps there is going to be a Nobel Prize for the particular thing of metamaterials, meta surface. But you never know. I mean, I don't know.
Because thank you very much, that all these ideas, I'm not expert in plasmonics, but more expert in magnonics. So practically all what you were talking about 10 years later was used in other big field, which I also take part of this also. I have many other directions, but in magnonics. So thank you very much for the talk and everything.
Okay, thank you for that.
So Julio, as he said, he was graduated in physics from the UAM in 1985, PhD in 1991, I guess, under the supervision of Arturo Baró. Then he was a postdoc in Berkeley with Miquel Salmerón, and then in Purdue with Ron Reifenberger. Again, this is important. I mean, Miquel was one of those people who, as I mentioned before, who Nicolás Cabrera brought here. Unfortunately, because many people went to make stays with him in Berkeley, okay? But he left the Autónoma and he went there. Julio was making a postdoc with him. I'm not giving numbers, but Julio has a very large number of papers, research works, and patents, and very, very active, intense outreach activities. On the top of that, and I think that was part of the prize in innovation that he got from the Royal Society and the BBVA Foundation, he has founded 2 companies, Nanotech Electrónica Sociedad Limitada and Nanoinnova Technology GmbH, right? Sociedad Limitada. And actually, I must say, I mean, Julio, and I know him because I have interacted a lot with him when he was director, when we were simultaneously director of the 2 departments. He's very committed to the UAM and then to the excellence also in the UAM. And I mean, he will do everything just for the sake of helping other people and people in his department, and as well on the physics and the science faculty. Now, quoting again the prize is the Physics Innovation and Technology Award, who was given to Julio Gómez Herrero, the Department of Condensed Matter Physics, Autonomous University of Madrid, again translated to English. The jury highlights his extensive career in the field of nanotechnology, with extensive work as a leading researcher in these studies and in the development of advanced devices that allow matter to be explored at the atomic scale. The instrumentation developed, as well as the knowledge generated, has driven the creation of technology-based companies specializing in this field, which have benefited both academic researchers and emerging industries in the fields of electronics, health, and energy. Julio, the floor is yours too. Thank you.
Okay. Yeah, okay. Thank you, Luis. Thank you, everybody, for coming. Let me start as usual, as FJ has finished. about the idea of giving a Nobel Prize for application, for a theory that has application. I think like 9 years ago, a Nobel Prize was given for the discovery, for the measurement of the gravitational wave. As far as I know, there is any application for this, but it's a beautiful Nobel Prize. I think it's one of the best Nobel Prize in physics because it confirms a theory that was already almost 100 years old. And the other thing is, you know, this NVIDIA company that fabricates video cards. To what? Basically to kill little Martians. Okay. Now that thing that it was started like 25 years ago, now is at the base of the most important research in humanity, that is artificial intelligence. So please don't tell me what is important for technology or what it is not, because it's impossible. The important is knowledge, and with the knowledge, that is what we have to generate, we will create things. Okay, so let me start with my talk. Well, why this talk? This talk is because, well, I'm trying to explain why or how we create nanotech. And we create nanotech for something that was, I mean, just pure work at the lab, okay? I was working at the lab doing something, and because finally, eventually, it happened that it was useful for something, but I didn't do because of this, okay? I did because I like it. I like to work, and I like to work in science and do things. But I didn't think, okay, let's do that to create a company. No, it was not the way it worked, at least in my case. Then I will talk about nanocontact. Why nanocontact? Because many people in this audience, theoretical and experimentals, work in this nanocontact in the 90s. And this is the very basic regions because we developed the electronic to work in nanocontact. Then we never work in nanocontact with the electronic that we create for nanotech, but at least it was the reason. Then I will explain something that is important to understand nanotech is data acquisition. That is a technical problem for experimentals, but you will see why it's important for us. I will describe our results in carbon nanotubes, in DNA conductivity, nanowires, and finally, I will briefly describe 2D materials and NanoInnova. Okay, so but let's start with something. This is the way an STM works. Okay, so you have a tip that is following a surface. Okay, the profiles of the surface, and there is an electronic, and there is an electronic to keep the current constant. So you have a tunnel current, this one. And this tunnel current is exponential with the distance. And this very concept is common from many other microscopes based on this principle, like for instance, atomic force microscopy. Okay? And this is in principle, unconnected experiment. I'm showing this experiment because I love it. It's simple, and it's what you can see, it's a science. It's just a drop falling from a faucet, and you have the drop is water with glycerin, and as you can see, it's forming a neck. There is a necking process, and this necking process is self-similar. So that's the reason because of the experiment. Okay, so it's in principle is unrelated with what I'm going to show now, but maybe not so unrelated. This is glass. Okay.
When glass is heated, it gradually softens. And when it's soft, above about 1400 degrees Fahrenheit, it's infinitely malleable.
Yeah, do you remember the previous slide? Okay, it's the same, but not with water, but with glass. And this is the same. The difference is because I don't know this guy, and I did yesterday that thing with Ruben. Okay, so and what it is important for my presentation? Well, this is not FJ, obviously, but this is an optical tapper. So you have a glass, and you are continuously stretching the glass. And as you stretch the glass, the number of modes that fit in this cavity get smaller and smaller. okay? And each time you have less and less modes, okay? So this, finally, when the taper is small enough, there is no more propagation anymore, okay? But this is light. So, sorry, can we do the same with, the question now is, what about electrons? Electrons are wave. So, but there is a small difference, is the wavelength, okay? So let's assume the free model for the free electron model for metals. In a metals, you have free electrons, and well, according to de Broglie, you have a wavelength. What is the wavelength of the electrons? Well, you have a Fermi energy, and using the de Broglie equation, you can easily find out what is the lambda of the electrons, and it's about 0.5 nanometer. So for green light, the wavelength is like 500 nanometers. So we have a factor of what? 1,000. So we need a taper that is 1,000 times smaller than the previous that I showed you, okay? So with just by stretching glass, you can make a taper that doesn't transmit any mode. But this is not possible with atoms, okay? Because we are talking about tapers with the size of one atom. And to understand the thing, well, this is a model for graduate physics. Okay, this is a one-dimensional box, and you have modes. Okay, that's the first mode. But you can also have the equivalent in 3 dimensions. This is a box, and well, the dimension along the x and y direction are about the same. But then we have a very long direction that is the C. So, meaning the implication is that we have a quantization, we have discrete levels in the x and y direction, but not in the C. Okay? So, but this is like a taper. This is like a taper for electrons. And then, well, this is a classical picture that I would like to show every time I give a talk like this. Okay, this is my department about the 84, okay? This is Nicolás García, Luis Oyer, Rodolfo, Arturo, my physics advisor, and Mole. Mole passed away a few years ago. But he published this paper, and what he did is, okay, this is the box. We have this box. This box is not a cylinder, but it has it's very narrow at the center. Okay, and let's calculate what happened with the modes of the electron that goes through this taper. Okay, and for this, the only thing he did was to solve the Schrödinger equation for this particular geometry. And well, then there is this Landauer modes, this Landauer conductivity that is quantized. So for each mode, you have one of these G, okay? Being the smaller one, this one, okay? This is the quantum of resistance, of electrical resistance. And this quantum of electrical resistance, to give a number, is like 30 kilo ohms, okay? So, but this is the thing. So as we have modes, like in the taper and in the optical taper that I showed you before, we have a conductance quantization. And this is continuous, okay? As you stretch the box, you can create quantum conductance. So I try to do this. Well, this idea is what I tried to do with Nacho Pascual in the 90s, at the beginning of the 90s. So we want to build a taper with a metal wire. And this metal wire is tungsten. It is known that with tungsten, it is very easy to fabricate very sharp tips with electrochemical etching. So you can see it. We have a film of a solution, of a chemical solution, and we made electrochemistry to reduce the diameter of the taper right there. So unfortunately, well, this is the taper. This I took with an electron microscope, and then we ran current. And as we ran current, we had electromigration. And with this electromigration, our idea was to make this taper thinner and thinner. But the problem, and this is an electron microscope, this is about, well, this was about less than 1 micron, okay? But it never worked. And this is what happened with 90% of my ideas, never work. But maybe it was not so much wrong, because recently they made this with gold, and this is like a tupper, and they use also electromigration to reach a very thin tupper, a metal. This is gold, okay, and it was so thin that this is like 20 nanometers. So, well, anyway, something that I would like to say is that I published this paper and I got 1 citation. But I work a lot, okay? I work a lot. At that time, it also happened that this paper from Maimin and co-workers in IBM, they published that they can create like mounts using an STM tip. The way they did it is they have the STM tip and the sample, and they apply a very high voltage. High voltage means 5 volts, okay? And then the tip just blow up. Well, they didn't say blow up. They say electric field evaporation. Okay, but it's the same. Okay, and they create this protrusion, these mounts, and the size of the protrusion was typically about 10 nanometer width diameter and like 2 nanometer height. So we did the same because, okay, we want to repeat the experiment. And then we realized that, okay, we apply the voltage in here, then the current is in an STM, okay? Then the current was saturated. And then as the feedback tried to recover the current, then we have jumps. We have jumps in the STM current, okay? And those jumps occurs at multiples of the G naught that I shown you before. Okay, and then, well, this is the idea. In fact, I think, look, in here we have this process. The red is the tip sample bias voltage. So we would just make a pulse, okay? And the black is the current. And we have the electronic with a feedback. So the electronic tried to recuperate the previous current that was like 1 nanoamp. So we have the tip that it was in tunnel, like 5 angstrom away from the surface. Then we apply the voltage pulse. We create the atomic neck, and the electronic withdraw the tip because the current was very high, and we have a feedback, and the feedback tried to keep a constant current, and the constant current that the feedbacks tries to keep was 1 nanoamp. And in here we have like hundreds of microamps. So this was our continuous view. Remember this idea about the glass and the paper from Mole? Okay, but the reality is this, because the wavelength, the Fermi wavelength, is about the diameter of 1 gold atom. This experiment was done in gold. So by the way, at the same time, and I didn't know it, Nicolas Agrite, well, we learned it, okay, was doing similar type of experiments. And we also published another one, okay? But the reviewer question was, okay, so you have jumps in current, and those jumps are because you have just atomic rearrangement, or are related to this, you know, Juanjo point of view. So our question was both. Of course, we have atomic rearrangement, but we have also jumps in conductance that reflect this quantum conductance predicted by Landauer. Okay, so we have both. And what we have now is, instead of having a continuous taper, we have a taper that jumps that way. Okay, and each of those jumps is about 1 atom size. Okay, and then of course we have confinement. We have confinement, but we don't have confinement of a light wave, but of electron wave. Okay, so those are the modes that can propagate in here, and so on and so forth. That is the same idea. But now we have modes that translate into conductance jumps. That is written there. Can we do the same with electrons, but without these jumps, without atoms rearrangement? The answer is yes. You have to use a semiconductor. In a semiconductor, you can control with a gate the number of carriers. And with the number of carriers, with the density of carriers, you control the wavelength. And you can have extremely long wavelength, like hundreds of nanometers. And then you see the atomic jumps, the conductance jumps in this semiconductor in a continuous way. Okay? So, and this experiment demonstrates that you have quantization in the same way as you have quantization in a optical tapper. So there are more experiments. It's Nicolás, it's Gavino, Alfredo, Juan Carlos, many people in here which are who are in the audience now. This another experiment was also important, but difficult. Okay? They correlate the jumps in conductance with the jumps in forces. Okay? And this is my experiment, my particular experiment. This is Juan Carlos Cuevas sent me this nice, this nice movie showing one of those atomic tappers. And this is magnets. This is my hand, by the way. So you have magnets, and I'm just pulling up so I'm building one of those, but see? By the way, this is, you see the, oops, I'm sorry. You see the atoms fluctuating here, okay? This is because this simulation is done at finite temperature, because theoreticians always want to be in the condition of the experiment. But this experiment is done at zero effective temperature. So we don't have this fluctuation. And this is because this is the reason because we have atomic chains. Okay? Then people observe atomic jumps at low temperature, atomic chains at low temperature. So this is, well, now I will describe something that is extremely technical. This is data acquisition. This for theoretician maybe is a bit boring. Well, I did a thing with my friend José María Gómez Rodríguez. He also passed away a few years ago. The thing is that when you have an analog signal like this wave, you can convert this signal to numbers using an atomic to an analog to digital converter, and then you have the signal in your computer. The other way around, you can have the signal in your computer and convert it to an analog signal. And this is something that is in this in a cell phone, in a mobile phone like this one, you have those things. You have an ADC because when you speak, you translate it to numbers that is inside the phone. And the other way around, when someone sends you an electromagnetic signal, the voice is converted through one of those DACs. Okay? And the typical thing for data acquisition is this. This is a modern oscilloscope. This is a digital oscilloscope where you use an analog to digital converter to have the signal on the screen. Okay? And this is the other way around. This is a function generator. You use a digital to analog converter to send a signal to the oscilloscope. But this is, I would say, this is non-smart digital data acquisition because what you do is you acquire many numbers and a string of numbers, but you cannot process number by number. If you want to process number by number, you need something different. You need something that is called, wait a minute, yeah, this DSP board, okay? But why this is important for us? Why this is important for this nanocontact? Well, I tell you the reason. Remember, we have an STM, and in a STM, you have, like this one, you have a tip moving through the sample, and you have a feedback, okay? And this feedback ensures you that the current is what you want to be, like, let's say, 1 nanoamp. But in many cases, as for instance, for those experiments with constriction, what you need is to stop the feedback and to approach the tip to the sample. And that way you can build one of those nanocontact. But this is extremely difficult to do with an analog electronic, with an analog controller. And in the 90s, this is what we had. We had analog controllers. Then we have to move from this feedback situation to this situation where the feedback doesn't work. The feedback is open. And for this, you need this. You need data acquisition, smart data acquisition, where you take one data, one voltage, you process with a computer, and then you get a number. And this number is what you put in the output, okay? And you output a number. And so the thing it works is, this DSP is a dedicated CPU. So it's a computer. It's a computer inside another computer. So you have a shared memory between the computer and your DSP, okay? And with this, you can take a voltage, do whatever you want, process the voltage, and put the voltage out. And this is a feedback. Okay, so, but also you can stop the feedback just by changing your code, by changing this calculate C current, and do whatever you want. And this is extremely powerful. And this was, why did you get to this solution? We get to this solution just by serendipity. I met a guy, it was someone selling electronic devices, and he told me about these DSP boards, but he didn't know anything. He was, he just sold the things. But he told me that this guy in the electronic engineer in here in Madrid knew a lot about. He was doing speech recognition. Okay, so Chema and I went to visit him, and he explained us how these devices work. And then, okay, this is the original DSP that we use. It's called C32, and this is a voltage amplifier that we need to drive the pieces. And this was done in here also, in Sega Index. And this is the start of nanotech. Okay, it's not the only thing, but it's very important for nanotech, this knowledge. Okay, and with this, Chema went for a postdoc, then I went to Grenoble, and I took one of those electronics with me, and we got these nice results. This is me in the ultra-high vacuum with this. This is the silicon 7x7. It was like a quality control from an STM. Eventually, in the 2000 year, we told the Autónoma that we have this business and we want to found a new company, and we publish a calendar with images of many people. This image is an image of a carbon nanotube with 3 contacts. And Raúl Villar said, the rector said, okay, do it. So we did it. This is Jaime Colchero, but this is Arturo Baró. This is Jaime Colchero. This is the mechanical head for an atomic force microscope. Two different designs. This is the older one. Well, the older one is not the older one, but it's one. And this is the software. And well, I'm writing this number, not because I'm proud of it, that I'm proud, but also because I want to transmit you that if you do technology, you can also have acknowledged from the scientist community. Okay, this is probably one of the most cited papers in our university. This is nanotech team, like in 2007. Here is Pablo Ares. Pablo. This is a technician in our department, Ignacio. Ignacio is, by the way, the first author of this software. This is a technician in Sega Index. This is the same nanotech, but now in 2014. This is Adriana, that he was the director of nanotech at that time. And this is Arturo, and probably you know this guy. Also this guy and this other guy. Well, and we did many things, and we had many ideas, and we sold a system worldwide. And now still we are still developing things. This is a new head. Okay, this is a new electronic, a new controller. So back to science, very quick. So you can buy 1 meter of monomode optical fiber for €1, less than €1. What about a monomode electrical wire? Can we have a monomode electrical wire? Yes, we do. And the way we measure it is using a FEN tip covered with gold to measure along the molecules, and this is the example of a perfect two-mode electrical wire. It's a carbon nanotube, and this is the resistance of the carbon nanotube as a function of the length at low voltage and high voltage. And this is the resistance. This is, by the way, those two papers are with FJ. This is the resistance as a function of the length in the presence of defects. Okay, we radiate the carbon nanotube, we create defects, and we observe that the resistance of the carbon nanotube increases exponentially with temperature. And this is known for Anderson localization, and it's a very important thing. We also did things with 2D materials. This is with graphene oxide. We reduce it and we improve the electrical conductivity. We create another company, NanoInnova, with Rafael, Felix, Tomás. He's a technician in inorganic chemistry, and myself. This is web page. We look for unconventional nanowires at the beginning of the century. It was published that DNA was an electrical wire, was an electrical conductor, but we tried very hard, so hard that we broke the DNA. This DNA molecule is contacted to a gold electrode. So we touch with a conductive tip. We try to see if we can measure any current. We couldn't. I collaborate with Felix and with Pilar with something that is called MMX wires, which are wires that the chemist can synthesize, like this one, and they conduct electricity very high, like in here. And let me show you the very last thing that I have done with atomic force microscope at low temperature. This is an experiment, something that we did in collaboration with Ruben and Ivan, many people. I'm showing this image because I love it. I simply love it. It's so beautiful. It's so nice. This is the experiment, and this is the theory. Well, you have to ask Ruben if somehow what he did to get this amazing similarity. This is, by the way, a grain boundary. This is a grain boundary in graphite. This is a nanotech. To me, this local oxidation on silicon represent very much nanotech. It was a combination between idealism and realism. Well, this is the last slide, but it should be the first. This is the experiment. This is the microscope that I used to work with this microscope at the beginning of my thesis, and now it's in a museum. So this is the lady taking the microscope to the museum, like me. Probably I will take to the museum very soon. So let me finish with this. Thank you for your attention.
Thank you, Julio. Thank you very much, Julio. Very nice talk. Questions, comments?
So tell us a little bit more about the story of nanotech. So at the end, essentially, it's not existing anymore. So
no,
something went wrong, I assume.
Well,
so.
something went, yeah.
And you're still working as a professor, okay? So it means you didn't make so much money, right?
Well, in a sense, to create nanotech was easy for us. We didn't, it was not a risky business. But in the other sense, we paid the salary for, let's say, 14 people for. No. We just fabricate one electronic. Well, we put some money, but marginal. Okay. So what we did is we fabricate a system and we sold it. And with the money that we got from this system, we sold two, and so on and so forth. And then we create nanotech. okay? But as I said, it was not, Arturo was more in the business, okay? Okay, he was Catalan. He is Catalan, okay? He's more in the, but I was a student and I love programming. That's one thing. It's not that my relation with programming is like these two. I'm not good at programming, but I love it. It's like those two guys that met each other and one say, I love playing poker and losing and winning. Oh, winning might be fucking awesome. So this is my relation with coding. Okay.
Any other question from the young audience or for the older audience? Anybody? No? Yeah. John first here.
Oh.
Thank you, Julio. Thank you, Julio, for the talk. But let me know, especially for the young guys, that to analyze or to realize how has been your career, your academic career is easy because you can check Scopus. But the impact of nanotech is not so easy. And let me say that a lot of groups in Spain make a huge advance of being part of nanotech because we have reached a level very competitive in comparison with the rest of the world that could be impossible to reach without nanotech.
I'll pay you the next coffee, Agustina. Thank you very much.
Next one is for free, so the over next. Any other questions? Yes, Ruben.
It's a very short comment because I think that, Juan Carlos was asking you, and I would like actually to tell something that is related to things that you have said and also FJ has stressed. I think we all do these things for fun. But at the end of the day, it's good to keep an eye and see, maybe they can be useful.
Yeah.
Sometimes you need to make the effort of doing it.
Well, we do it for fun, but it's good also to have a salary.
Yeah. And that was my second question, that my comment more than a question, following what it was said in the audience. Nanotech was not able to survive the crisis, the economic crisis. So, and that what reflects is the weakness of the Spanish industrial system.
Yeah.
Nanotech was relying heavily on funding coming from Spain. That was cut during those years of the crisis. It was very difficult to survive with that. So, and no one did the effort of actually saving these things. And you know how hard it is to put these things up and then how easily they disappear. So this is simply a message that this is something that we have to nurture, this entrepreneurship.
Yeah.
And we have to convince our authorities that it's worth to invest a couple of bucks, not more, in this kind of efforts. That was my only comment. Because, the audience,
you know something?
The year that nanotech existed, it played very significant role, as Agustina was saying.
You know something that I like? I like the idea of, okay, and winning a salary, and it's probably a good salary in Spain. So, but somehow I return this salary to the society because I pay the salary of, well, not only me, okay? I pay the salary of 14 people for 16 years or whatever. So, and this, when I go home and think about that, I'm happier. Thank you.
Well, I think the way to change that is change community, I guess, or vote a different thing for the next time.
Vote a different thing can be a good idea.
For the next. So I think then in the name of IFIMAC, yeah. Sorry, Jaime.
Oh.
This is something we should talk, but something I think is a pity. Nanotech, in a sense, still lives, right? You have done new electronics, which among friends. So how many new electronics are there around? 50?
Yeah, about that.
I have 3. You have quite a
lot. It's about
they
that.
work very nice, right? And we should try, and that we have discussed a lot, and I think we are close to have a kind of new head. So something with regard of you were discussing doesn't work in Spain if maybe you have one cupboard with where you can make a new electronics, another one where hopefully you can 3D print the mechanics and order the optics, and this doesn't give a company.
Yeah.
Right?
For this, you need.
So there are quite a few points, which is not only financiation, but I think in Spain it's quite difficult to make a company from university, and this is a pity, and we should think about it.
Yeah.
And I think Julio and I know what we're speaking about. Okay, so thank you.
Look around again. No more. So then in the name of IFIMAC, and actually also in the name of the Spanish Royal Physical Society, which I'm representing here today. By the way, I know that one person already made himself member. I will not mention who he is. It's around there. So we are missing 2 to reach 4,000, right? So you are welcome to the society. So and now we have the lunch at in Plaza Mayor, right? And we reconvene here at 3:30, okay? So thank you.